Thank you for coming. So it was awesome several days. Hope you have a bit of energy for yet another talk. The talk shouldn't be complicated though. Let's start. First of all, I'm Slava. If you are looking for complication, full name is Svyatoslav, but Slava is also okay. Here's the short recap of my story, which is kind of relevant for the talk. In the latest years of my uni, I joined Yandex Ads infra team. Yandex is a Russian company, which is kind of Russian Google. And it was huge project, something like 20 years old. I worked there several years and moved to Yandex.Search infra. This is an even bigger project and with larger code base. And around 2 years ago, I changed the project again. And now I'm working on projects with insane amount of code. So I took a look on all these sort of huge projects and noticed one interesting thing. There are tasks which are simple when code base is small and became really complicated and interesting when code base is huge. And that's specifically with the code. For example, new CPP standard feature arrived and you want to migrate your code base to it. If the code is small, you're just doing it in 1 seat and 2 seats every evening. And after that, every new commit just follows the already existing code and everything is okay. Once you have, I know, at least 100,000 lines of code, it's became complicated. And essentially, sometimes you don't know how to approach it. And another very similar type of problem, you decided to switch widely used API in your code. And you hit in exactly the same problem without changing the standard, without changing compiler. And just because the amount of code is huge. And sometimes you just meet tasks where you organically want to practice regular expressions over your code. And that's kind of common. I don't know. I'm meeting something like this once in a quarter, once half a year. I've noticed all this and start thinking, maybe this isn't just the large company's disease. And once you are living in open world, it's not so an issue. So for this, let's make a quick check. Wave me by hand if your project at least, as I said, 100,000 lines of size. Okay, cool. Wow, everything. Everybody. I thought it's going to be less. And second one, now only those ones who are not working in huge companies. So for example, less than 5,000 people. Less than 1,000? Okay, good enough. So like now we have a third. So the problem is real, and it's definitely real in corporation and big companies. And as we see, it's real in smaller size. So we have a problem. We have a set of devs who are encountering this problem. Let's try to think how to make life simpler here. And the answer is funny, at least the answer I'm proposing. Let's try to treat code as a kettle, which is just a funny name for let's try to automate everything what we can. But automate what? You can't automate everything with the code. So I've formulated 3 types, 3 large branches of tasks, which I'm going to tackle today. The first one is find. We want to find something in our code. Obviously, this is going to be something more complicated than just the substring of variable with given name. For example, we want to find all function declarations with const stud string reference as an argument. The second one is fix and enforce. By the way, this one was discussed several times, I think, even on this conference, but the idea is the following. We have two stages. In the beginning, we want to fix our project from some undesired state to a desired state. I don't know, migrate to a new standard feature. And after that, we want to enforce those code which we already fixed to not degrade back. An example, we have awesome concepts, and we want to eliminate most of std enable if from stud enable if from our code. Let's do it. In the beginning, we're fixing our code, and after that, we're checking that fixed code do not degrade back. And the last one, which is the most entertaining, by my opinion, is to generate something. It's hard to explain in one sentence, but the idea is following. Sometimes you need to write some code, but this code is not particularly new. It's somehow a transformation of an existing one. Usually these tasks are like not once in a while, and it's hard to describe them in general, but let's consider a simple example. We want to serialize an enum, like taking 0 and returning green, taking 1 and yellow, etc. So this is a enum, and we want to write something like this, trivial. And if we take a look into this code, there is nothing really new here. For the first row, we need just the name of enum. But the name of enum already written in our code. After that, we need a bunch of cases. And each case is exactly the same. We just change the name of enum value. So if we would have a good tool for it, we can just script it. We can write a script which is taking the existing code, and after that generates enum serialization. Obviously, I'm not proposing to use some advanced technique for this, and hopefully, eventually, we'll get the reflection which will allow us to do it inside of the language and not outside of. But this is kind of example of generate. We'll get to more close to real life example in the end of the talk. Okay, so 3 tasks for today. But before jumping to try to solve them, let's try to understand a bit of theory. Theory is not going to be too boring, so not fall asleep. So here's a spoiler. So I'm planning to talk about some tools. We are going to use some tools. But they are somehow advanced. Maybe existing tools are already good enough. We have an awesome, really old text processing tools, grep, sed, even scripting languages. Why it's not enough? Why we can't solve a reasonable amount of problems just by using them? Maybe we need to just practice sed better and everything going to be okay. For this, let's take a look into the following imaginary example. You met or wrote code like this. Probably you found it in codebase. It's going to be more realistic. This is just a worker. And worker doing 2 things. In the beginning, it's wait for something, wait with conditional variable, and after that, doing work. There is quite well-known bug here. Let's anyone shout. Bingo, it's furious wake up. And this is those sort of bug which is well known, but you sometimes forget it, or sometimes you meet people which hearing first time about it. So that's why it's a good example. This is furious wake up, and what is the problem? Conditional variable can wake up not because it was notified, but just by coincidence. Just it's happened. And there are several ways of fixing it. My favorite one is like this. There is overload of wait, which accepts 2 arguments. And the second one is a functor, which checks that condition which we were waiting is ready. And if we are not, you just go sleep again. So if suppose you first time met this problem and decided, okay, I want to enforce never this happening in my code base again. At least let's try to find all places where this happening in my code base. And we're trying to write a grep for it. So let's try to do something like this. So minimal viable example. We are searching for weight, string, after the parenthesis, and any amount of symbols inside without a comma. The idea is following. If it's going to be 2 arguments, there are going to be comma between them. So we will probably match most of the stuff we want and don't match to call of weight with 2 arguments. And we'll find some C function somewhere in forgotten place of our code. We will find some debug output, which by coincidence has this signature. And we won't find some places which we need. So like here we see that formatting split call of weight on several lines, and we can't find it because closing bracket on the other line. So all this happened to you, and depression come. And okay, and actually this is to some extent real story. I really saw attempts to fixing some large refactoring tasks, so debugging tasks based well tools like this. But being depressed too long is a bad idea. Let's try to understand what went wrong. And went wrong the following. Code is a complicated thing, and it has internal structure. And complicated internal structure. We have types, we have condition, we have cycles, we have variables, etc. What we actually were looking for is call of method weight on a variable of type stored conditional variable with 1 argument. And now we want to understand how to express this structure in our tools. Where to find structure to use it in our tools. Okay, we are software engineers. Let's parse our source code, extract this structure, and after that write in tools with this structure. Here's an obvious problem. If you actually sit and start doing it from the ground, you won't finish in a day, in a week, in a month. I don't know. I heard the talks about writing C++ parser, and this was several years effort. Thankfully, compiler already doing this for us. Let's take a look into the compiler process high level and try to understand where to chime in to get structure we are looking for. Everything starts with source code. After that, we are running preprocessor. So substituting includes, expanding defines, etc. After that, we are parsing our code. Over parsed code, we are creating intermediate representation. After that, we are running optimizer and assembler and getting object file. And we link object files and get our binary. And we need some place in this compilation process where structure already extracted, but we still have a connection to original source code. So we can say that this if came from the specific place in the code. And surprise, surprise, this place is after the parsing and named AST. Let's take a look into the AST in real. Here's a Godbolt, and obviously we agree on any cookie. And here's a simple code. We have a main, which just declares a variable, returns 0. And on the right-hand side, for you, still right-hand side, we have an AST. AST is just a tree representation of our code. The root of AST is translation unit declaration. Building in C++ is per file, per translation unit, so the root of AST is translation unit declaration. And now in my translation unit, there is one function, and we have one child, which is function declaration. And we know that this function resides on the line 1 to 5. It's named main, and we even have signature of it. Children of this function declaration is a compound statement. Compound statement is curly braces and any amount of statement inside. One of them is declaration statement, second one is return statement. Everything somehow obvious. The only interesting part to look is this plus. It's inside of initializer of the variable, and it has 2 children. That's the only interesting part about the plus. Cool. We have some candidate where to get this structure. We have an AST, Clang AST is awesome. Let's use it on our tools, in arbitrary tools. But how? And there is an awesome answer named Clang libtooling, which allows us to interact with internals of Clang. To take a look, to talk about the whole libtooling or one talk impossible, we are going to talk about 2 things. First one is Clang matchers, second one is clang-transform, and a bit of Python bindings on dessert. So essentially, this is technological plan for today. We have our task for today, we have our technological plan for today. Let's go. The first task, find. We're trying to find something in our code. There are 2 possible approaches to do so. The first one is to create a DSL, which will allow us to express which piece of AST we want to find. The second way is, okay, as I said, we are software engineers. Let's give us an AST in a machine accessible way, and after that we will find everything which we need just by writing a script. Both of them are possible. We are going to talk about first one because it's going to be useful for the second task. First one means DSL. DSL named Clang matchers, DSL domain specific language. And here's a solution for weight problem. We want to match. This is a letter M, the only usage of M. Call expression where we call C++ method which holds following of this. It's named weight and it's on name stored conditional variable. And it has 1 argument. So essentially exactly those definition which was in the beginning. The second task, we want to find all lost exception in our code. There are code base where there is a policy that you can't swallow exceptions except in specific places in the code. For example, you can swallow exception in main, sometimes you need it. You can swallow exception inside of some core class, but in all library code, you need to propagate it one way or another. And we want to find places which violate this policy. And our typical client is going to look like this. We are doing something, after that we are catching and not rethrowing. The first approximation for the solution is going to be like this. We want to match catch statement if it doesn't have a child, not direct child, but somewhere in the subtree, we have a throw statement. Here's kind of 2 specific interesting things. First of all, we won't match this. In AST, there is throw, which is a child of this catch statement. So in terms of AST, we have a possibility to throw. This is false negative, but still it will catch reasonable amount of important things. And we will match something like this. And it shows an interesting limitation of matchers. Here we are calling function always throw, which by the name should always throw. And we essentially throw through it. But this function can be declared in different translation unit. As results, we know nothing about it inside of our AST. So with matchers and with working with AST of this translation unit, we have no chances to make any statement about it. That is locality of matchers. Now let's take a look that it's actually work with this example. Okay. What do we have here? We have some two empty functions. After that, those code which we saw on a slide. And we include an exception. Here is a matcher we saw on the slide again. And here's a Clang query. Clang query is a tool which allows you to debug matchers on your code, and you can run it inside of Godbolt. And we are doing so. Surprisingly, we see two matches. The second one is expected. It's our code. And the first one is something inside of exception PTR. Why the first one? As you remember, creation of AST happens after the preprocessor. Includes expanded inside of preprocessor. As a result, everything which you include in your code will be reflected in your AST, and your matcher can match it. Let's try to fix it a bit. We still want to match the same stuff, unless in system header. Boop. Hopefully I remember it. Error parsing. What does it say? Oh, probably I haven't closed the all of. Yeah. Okay, cool. So what we said, we want to match catch statement unless they are not in a system header. And we see only one match which we found. Now let's rethrow. And there is nothing here. Okay, cool. On the C++ conferences, especially on talks like this, I see something in Godbolt and I scratch in my head and start struggling how to actually run it over existing code, how to do it with the project which is inside of my repo. Let's take a look at it. So first of all, we need to get a Clang-tidy which we were using in Godbolt, and you can install it from your packet manager or build with inside of LLVM. It resides in Clang tool extra. So I pre-build it, and we are going to take a look and query example. Here we have some trivial code. So this is some main, which have some function call, some output, etc. Okay, so this is Clang query which I built, and let's run it over main, and let's match anything. For example, all function declarations, and we have tons of stuff. Let's match our specific function, and here it is. So you can run a matcher, you can run a Clang query over your existing code, and after that debug matcher on your specific on your code. And that is amazing. So like when I start touching it, it was like, wow. To sum up and essentially this is close the find problem. The run matchers. This is a declarative language to query some piece of AST. And we can use Clang query to debug matchers on an existing code. And if we think a bit, matchers are mostly enough for enforcing something inside of your code base. You can write a matcher which matches those code which you don't want to see. I don't know. In case of std enable if, you can write a matcher which matches std enable if. And after that, write the following sort of CI check: Clang query on the changed file, matcher, and if you have at least one match, check has failed. Yeah, it's actually kind of going to work. Not an optimal way. Optimal way in the next task, which we fix and enforce. Okay, fix and enforce is the most common one. It's like all auto-refactorings, all code compliance resides here. But the most, I don't know, easy example is new standard feature. But as I say, two-part. In the beginning, we fixing, after enforcing, and main character today is clang-transform. And clang-transform is a framework or library inside of libtooling, which allows you declaratively describe what you want to change and on what you want to change. And start everything again from the matcher. Let's consider an example. We have a function which originally was created with a pointer argument. Time go, eventually we realize that pointer is never null pointer anymore. And we want to express it inside of our code. And we create in reload with reference. And the amount of code where you have function with pointer, function with reference, and one calling each other, I don't know, in every code base I met, there is something like this. And one of them is sometimes commented, okay, it's never null, please don't use it. And we want to uniformly migrate our code base from one to another. Essentially, we want to stop calling with pointer and start calling with reference. First of all, let's match what we want to find. We want to match call expression, which calls function declaration, which has name awesomefunc, which has 0 argument, which has pointer type. And we want to bind this piece of st, which corresponds to the first argument, as an argument. Argument is just a string identifier. It could be anything, foo, buzz, or whatever. And we're just going to use it in the next part. Next part is declarative description of transformation. We want to change argument, this piece of AST which we say, to transformer, maybe the ref argument. This is built-in transformation inside of clang-transform, which is obvious trying to deref this piece of AST. There are reasonable amount of built-in transformation. We can insert something before AST node. We can add include to a file with AST node. We can take the whole AST node and change it to some hardcode text. We can change the AST node with accessing some field inside of the type. There is one interesting part here. How you can change AST node to some text? The answer is no how. It's not how it works. You're taking the AST node and after that, changing the source code which corresponds to this AST node. Why so? Because manually crafting AST is a complicated task. You can't do it. And even if you can, in the next standard, it's going to change. It could change. And your tool not going to be portable from one standard to another. And that's why you are going with a simple way. You are matching piece of AST and after that changing code, which like original source code. Okay. And now we are ready for essentially all meaningful code for doing this transformation. Let's take a look at it. We're creating the constant string, which is an argument. And after that, we're creating transformation rule. And this is the cornerstone of the whole tool. The first part is a matcher. And now this matcher is C++ code. And call expr is essentially C++ function which returns something. But this is syntactically exactly the same as matcher's DSL. And this explains why matcher's DSL looks like this. And change 2, as we saw, this is a declarative transformation. After that, we are creating a transformer, which takes the rule, and after that takes callback, which accepts generated changes. And after that, we can do whatever we want with these changes. In my minimal example, we are going just to iterate over them and apply to source files. Okay, so let's try to make it live. What do we have here? First of all, we have no diff in the repo. We have, again, some simple source code. We have some object. After that, we are calling undesired function overload, which taking pointer, and we explicitly taking pointer. And the second call is get singleton object. The only point, like reason of get singleton object here is to have some function which returning a pointer. Here's a definition of get singleton object. Again, trivial and 2 overloads. After that, we have a full code of the tool, but it's kind of not possible to read during presentation. But the meaningful part is still here. Create rule, create transformer, and after that, run transformer and apply all changes. You can find the whole code of the tool inside of my repository with examples, if you wish. But essentially, you're just taking tool template from the Clang tool extra, adding a few lines which want the slide, and it just compiles and works. Let's see that it works. Okay, so I have my pointer to ref pre-build tool, and I want to run it over main CC, and I get the awesome diff. This diff always, I know, inspires me. Now I can use the tool, which is actually understand what inside of my code. For the first line, we understand that, okay, this is just the explicitly taken pointer. I can delete explicitly taken pointer. And the second one, I can't do anything meaningful except adding the explicit dereference. One small piece which I need to add is compile comments JSON. This is a file which you probably know if you were using any Clang-based tool. That just describes how your project is built. So you have files, and after that you have a comment, and after that you have a directory which this comment should be called. We have just fixed our code. Okay, we fixed how to enforce. And the answer is simple, Clang-tidy, and we talked a lot about this in this conference. But the superpower of clang-transform, which I really like, that you can just take a rule which you have written for your change and create a Clang-tidy check from it. And if you really want, you can even apply the change from the Clang-tidy check. But obviously, you will have to build custom Clang-tidy with this check. What is written here? Some boilerplate and make rule. So we're just taking those code where we were creating our rule, putting it here, and everything works. So essentially refactoring the function. About fix and enforce. Clang-transform is like search and replace powered by Clang matchers. And the most fun for me is that you can declaratively describe which changes you want. So you're not writing some code, you're not iterating, you're just saying, okay, please do that. As you saw, we have some some built-in transformations, but they're not obviously cover all cases. Sometimes you have some complicated refactoring, which you can't do with these simple manipulations. And in this case, you fall back to Clang-tidy when you actually can write a custom code, iterate over the ST, looking something, changing something. And about that was the talk on the first day and even lightning talk. Clang-tidy support out of the box once you wrote your transformation. The main drawback, it's relatively hard build your first tool. You actually will need to check out LVM, change something inside of it, build it. Obviously doable even in a small project. And usually when you're writing something for your own, for your custom task, it's impossible to upstream this tool because it's going to be specific for your project. And you will have to support this change indefinitely while you're going to use this tool. But there are generic tools which already exist, Clang tool extra or inside of Clang-tidy. Before writing your own, check maybe you don't need to write anything. Okay, so this was the initial part, which somehow well discussed already, and this is my favorite part. Let's jump to it. Generate. As I say, generate is about writing code, but not particularly new. And now, real world task which I faced in my previous project, one of previous projects. We had tons of span object spread out over our code base. Span is just an event which could happen with your request. The most important part of a span is string description of what this event means. And as usually, we were attaching these spans to traces, after that sending traces to centralized storage and have tools which allows us to take a look into the spans, take a look into what was going on, have some statistics, etc. And one day, we've noticed that we are spending reasonable amount of CPU just compressing the strings, and meaningful amount of network bandwidth by just sending them to a collector. We thought a bit and, okay, let's try to optimize this stuff. Okay, how to optimize it? The intuitive idea is going to be like this. Let's assign an ID to every event, and after that, short integer ID. And after that, send over network only this ID. And create a tool or library which allows us to exchange this ID to original string afterwards when you're actually trying to look into this stuff. We can even store in the collector only these IDs. And here is some children garden implementation of something like this. We have some registry of all events. If simplified to the highest grade possible, this is just a huge enum which has one value per event. After that, we need a dictionary to exchange event IDs to original strings. Again, really simplifying, this could be a huge array which has one string on the position of the value of this enum. And we need a constructor from event ID for the span. And now let's take a look into this code again. If you think a bit, it has very similar properties as code for the enum serialization. There is nothing really new here. One asterisk. In our code base, all spans were created from string literals. Not essentially all, I know, 99.9. So to create this huge array, you need just to take all string literals from your code. Somehow work with all your code base, find all these string literals and put them in one array. After that, changing these spans to be created from enum value, you need a new constructor, and you need to make a simple refactoring, which will replace your string literal with a newly crafted enum. The only interesting part here was how to create names for these enums, for enum values. They should be unique over all code base. And one approach could be, let's concatenate somehow the long description. But there were poems inside of the descriptions. So it wasn't feasible. Thankfully, the name of span variables was mostly good enough. You can take, it's ended up in taking the whole names, like taking the name of span variable, taking the string literal, and after that creating the enum value for the event from the name, just like this, changing the formatting. And sometimes I have to make them unique forcefully or manually. If I have a clash, I know either adding some short unique ID or something like this, or manually going and fixing it. But it was several files, easy to do. If you would have a tool to do such kind of stuff, essentially this is one-time thing. I'm not going to convert all code base every now and then. I need to one time write a script which is going to do it and forget about it. And obviously nobody in the community need such a tool, because spans from string literal, come on. So I need one-time thing, and the huge spoiler is on projector. We have a pretty quite good technology to write such one-time things. This is Python libclang, which is essentially bindings from Python to some limited API inside of Clang. And you actually can poke the EST with it and do all those scripting stuff which you're sometimes doing inside of Python. And here is one of interesting function inside of my scripts in those time. What is here? We are trying to find all spans, extract variable names, and extract string literals. The first argument is cursor. Cursor is just an IP or part of API in libclang, which is pointer to the node inside of AST. And the result is output parameter, where I'm putting all stuff I found. If currently cursor points to the variable declaration and type of this variable is not span, I'm skipping it. Otherwise, I'm extracting a variable name. Here I'm actually poking the AST. And after that, I'm trying to extract string literal from the subtree of this variable declaration. And after that, appending result to my output parameter. And if the node wasn't variable declaration, I'm just recursively traverse my tree. So I know. Simple code. Let's take a look into this in a more wild example. Oop. What do we have here? First of all, we need libclang installed. And I have a virtual environment with it. And after that, file which has main file, now main create just 2 spans. And I have a span cc, which is a function which creates a span. And I have my example pipe. Some code to store the metadata about what I found. After that, find string literal, which is not really interesting. If I found a string literal, I'm remembering the source location and extracting the string literal. The code which we saw, find all spans. And after that, some output and boilerplate to run it. Creation of compilation database from our well-known compilation commands JSON. Let's run it. We want to run it over one file, which is main.cc. Okay. What do we have here? We found two spans. We have a variable name for every span. And the most important part, we have a location of string literal. And we have a message. Why location is important? So after I have in programmatically accessible way all this information, I can generate source code. So like I can create my huge array, I can create my huge enum, but one part left. I need to change the string literal with the my enum. And for this, I will need source location. So I will generate a huge replacement, and after that, there is a built-in tool, not built-in, there is a tool in Clang-tidy which allows you to do this replacement. Let's try to sum up a bit. libclang is awesome thing for fast hacking. And this is, I think, one of the main messages, I don't know, from the talk. As you can see, I'm not a fancy team. I was doing just infrastructure in several large products just. And probably I'm not going to face the task which I know could be really reused by a community. But I still can write a simple tool which will save me, 1, 2, 3 working days. The threshold is somewhere around this. If I need to change at least 500 lines of code, sitting and writing a script is simpler than just going and manually editing the file. And that is a message. But sometimes you need some more fundamental. You want to run your tools inside of CI. You want to check if you're doing fix and enforce. During enforce process, you are going to run your check inside of CI. And probably Python scripts is not the best fit for it by various reasons. It's hard to maintain, B, it's just slower. In this case, you're probably going to write in a custom tool or writing a custom Clang-tidy check. And now the message of the whole talk in one slide. Our project's huge, even if you are not in a fancy corporation. And you will meet repetitive tasks with code, where you're just not doing anything, just moving code around. These tasks now are far beyond formatting and linting. But formatting and linting is still a good part of it, but formatting and linting are already quite well solved. There is tooling inside of Clang which allows you to delegate this task to machines. And next time when you meet such a task, use this opportunity. And now we have something like 10 minutes for questions. Thank you.